Welcome to the SAR channel, where sound and audio are demystified. Digital audio systems use special processors to handle recording and playback. These processors work as converters. They change analog sound waves into digital signals for processing, saving, or sending, and then turn them back into analog signals so we can hear them again. In a linear PCM, pulse code modulation, system, the playback process basically reverses what happens during recording. This includes steps like fixing timing errors, decoding signals, separating data, correcting mistakes, converting digital data back to analog sound, holding output samples, and filtering the signal to remove unwanted frequencies. Before the digital to analog conversion, oversampling filters are used to improve sound quality. The playback system takes a coded digital signal and rebuilds it into an analog sound wave. These circuits must reduce any problems caused by storing or transmitting data. Storage media can have mechanical issues or physical damage. In analog systems, such problems must be fixed directly. For example, keeping a turntable's speed stable to avoid pitch fluctuations. Digital systems, though more sensitive to timing and bit errors, can use processing to detect and correct many of them. To handle timing variations, playback circuits use data buffers and perform error correction. Timing and clock signals within the digital stream are identified by time-based correction circuits, which help align the signal, separate frames, and determine the value of each bit. Since most received signals have timing errors, like jitter, devices such as phase-locked loops, PLL, and buffers are used to fix them. A buffer stores data as it arrives unevenly, then releases it at a precise rate, ensuring accurate playback timing. This allows samples to be played back at the same rate they were recorded. The encoded audio data is then separated, demultiplexed, and converted into NRZ, non-return to zero code, where signal levels represent binary values. This makes the data readable for further processing. Demultiplexing also restores the parallel format of the original data. The circuit gathers incoming serial bits and outputs full words of data at once. Error correction data is separated from other information, checked for mismatches, and used to fix any detected errors. If the calculated parity doesn't match the stored one, correction algorithms recalculate the right values. When errors are small, they can be fully repaired, ensuring perfect accuracy. If errors are too large, concealment methods are used to minimize their impact. By the end of this process, the data has stable timing, has been properly separated and corrected, and is now ready to be converted back into analog sound. Just as the analog to digital AD converter determines how accurately a sound is turned into digital data, the digital to analog DA converter determines how faithfully that data is turned back into sound. Traditional DA converters can have similar accuracy problems as AD converters. Sigma-delta converters, which work by measuring changes over time instead of amplitude, can reduce some of these problems but must use noise shaping to keep noise out of the audible range. Conventional DA converters process all bits of a digital word in parallel and can suffer from various linearity errors. The main ones are absolute linear error and differential linear error. Absolute linear error is the overall deviation from the ideal output level and should be less than half of one least significant bit, LSB. Differential linear error happens when the size of each step between digital values is uneven. This type of error doesn't affect loud signals much, but causes distortion at very quiet levels. Differential nonlinearity appears as steps that are too wide or too narrow, which can even cause some signal ranges to disappear. These errors are small for loud sounds but can distort weak signals noticeably. Because they follow the shape of the audio, they're easier to hear and identify. Linearity tests measure how accurately a converter reproduces different levels of sound. Linearity means the output signal's amplitude correctly matches its digital input value. Any nonlinearity causes distortion. Traditional ladder-type converters often show this problem because of tiny bit weighting errors, which can increase with temperature changes, stress, or aging. Some DA converter chips include built-in calibration tools to help manufacturers adjust and improve accuracy. Ultimately, a converter's linearity, not just its bit depth, is what defines how precise and clean the sound reproduction will be. There are different kinds of DA converters used in digital audio systems. Traditional converters work differently from sigma-delta converters, but are simpler to understand. A DA converter takes a digital word as input and changes it into an analog voltage or current as output. The most basic form is the weighted-resistor DA converter. However, this design demands extremely precise manufacturing, which makes it difficult and inefficient to produce accurately. A better and more practical design for a DA converter is the R2R resistor ladder. This type of circuit is simpler, more consistent, and can be manufactured efficiently. Zero-cross distortion happens where an audio waveform crosses from positive to negative or vice versa. Changes in current or bit switching speed can create small errors and glitches at this point. This type of distortion can be reduced by precisely calibrating the most significant bits using a sign magnitude setup or employing separate DA converters for the positive and negative sides of the signal. Sigma-delta DA converters do not produce zero-cross distortion. Many playback systems use 24-bit digital-to-analog DA converters to reproduce 16-bit recordings more accurately. This is because real 16-bit converters can't perfectly decode 16-bit signals. They always introduce some small errors. To achieve the best possible sound quality, the recording and processing stages need a wider dynamic range than the final audio format. The 16-bit word length used in CDs and similar formats was mainly chosen because 16-bit DA converters were available at the time, and using longer words would have reduced playback time. High-bit DA converters work similarly to oversampling. They don't add new information, but use existing data more precisely. For instance, oversampling a 16-bit signal at 44.1 kHz increases the sample rate and allows for more accurate calculations. A converter's quality shouldn't be judged only by its bit depth. Instead, its performance is better measured by signal-to-noise ratio and dynamic range. The dynamic range, measured between 0 Hz and 20 kHz with a minus 60 decibel signal, shows how well a converter reproduces very quiet sounds. From this, the effective number of bits, ENOB, can be calculated using this formula. For example, a 16-bit converter with a 95 decibel dynamic range effectively provides about 15.4 bits of usable resolution, meaning around 0.6 bits are lost to noise and distortion. Many modern systems use sigma-delta DA converters because they solve several issues found in traditional designs. Sigma-delta converters use extremely high sampling rates, noise shaping, and single or multi-bit conversion. A single-bit system produces a very fast stream of on-off pulses to represent the audio signal, while multi-bit systems generate a pulse-width modulated PWM signal. Because sigma-delta converters have high inherent noise, they rely on noise-shaping algorithms to keep that noise outside the audible range. Traditional converters still have benefits. Since they don't use noise shaping, they avoid creating high-frequency noise. At very low sound levels, their binary current sources switch less often, which helps reduce glitches and background noise. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Let's continue. Many digital audio systems use two sample and hold circuits, one at the input and one at the output. The input sample and hold captures and holds the analog signal during a deconversion, while the output sample and hold samples and holds the DA converter's output to remove unwanted switching glitches. DA converters can produce tiny unwanted signals or timing errors when converting digital data into analog voltage. The digital input may take time to settle, and not all bits change at the same instant, causing brief jumps or spikes in the output. Even fast converters can have these short glitches, which create distortion if not removed. The output sample and hold circuit fixes this by capturing the correct output voltage only after it stabilizes, then holding that voltage until the next sample. This creates a clean, glitch-free pulse amplitude modulation, PAM signal. The sample and hold circuit also corrects a frequency issue called aperture error, which weakens high frequencies because the output pulses have a finite width. Narrower pulses reduce this problem, but if the hold time becomes too short, the signal-to-noise ratio drops. An ideal converter would have infinitely narrow pulses, but this isn't possible in real systems. To correct for this, a digital or analog filter can boost high frequencies before or after the sample and hold circuit, resulting in a flat and accurate frequency response. When removing switching errors, the sample and hold circuit itself must not introduce new ones. During the hold state, it outputs a fixed value, but when switching to sample mode too slowly, it can create small intermediate voltages that distort the output. This issue doesn't affect the input sample and hold because it's not directly connected to the output, but in the output circuit, these errors become part of the final signal. High frequencies are most affected as their sample-to-sample differences are larger. To reduce this distortion, the sample and hold circuit should switch between modes as quickly as possible, ideally with a square wave response. Though perfect transitions aren't achievable, an improved version called an integrate and hold circuit allows smoother, exponential transitions between samples. This avoids distortion while slightly reducing high frequencies, which can then be corrected with equalization. Overall, the output sample and hold circuit removes switching glitches from the DA converter, minimizes aperture error, and ensures clean audio output. Some modern DA converters are designed to prevent glitches internally, making a separate sample and hold circuit unnecessary. In others, the sample and hold function is built directly into the converter chip, while aperture correction is handled digitally. In a digital audio system, the first and last circuits are low-pass filters, called the anti-aliasing filter at the input and the anti-imaging filter at the output. Though they look similar in design, they serve different purposes. Modern systems often use digital filters with oversampling instead of old brick-wall analog filters, but a simple analog low-pass filter is still used at the final output stage. According to the Nyquist theorem, the input low-pass filter removes frequencies higher than half the sampling rate to prevent distortion. Similarly, the output low-pass filter removes frequencies above this same limit, but its job is different. It smooths the stepped pulse amplitude modulation PAM signal from the DA converter into a continuous waveform, recreating the original sound. The DA output contains unwanted high-frequency artifacts created by the sampling process. The output filter, also called a smoothing filter, removes these components to produce a clean, natural analog signal. The design principles for output filters are similar to input filters. They must have a flat passband, strong attenuation in the stop band, and a steep cutoff slope, while minimizing audible phase distortion. However, the output filter must also handle the sharp transitions of the stepped signal. If its transient response is too slow, distortion or unwanted side effects may occur. Another consideration is that digital circuits can generate high-frequency noise in the megahertz range, which some filters may not fully remove. When sampling occurs, the original signal is multiplied by a series of pulses, creating copies of its spectrum at multiples of the sampling frequency. For example, a 1 kHz tone sampled at 48 kHz produces additional components at 47, 49, 95, and 97 kHz, and so on. Although the sample and hold process reduces these unwanted frequencies, some still remain close to the audible range. The output low-pass filter removes these image spectra, leaving only the true baseband audio signal. Even though frequencies above the Nyquist limit are inaudible, filtering them is still necessary. Without filtering, these high frequencies can interact with later stages in the signal path, creating new distortions or modulations that degrade the final sound quality. When a short pulse or impulse is sent into a device like a low-pass filter, The result you get at the output is called the impulse response of that filter. In general, the output signal of a filter is the result of combining or convolving the input signal with the filter's impulse response. For an ideal brick wall output filter, this impulse response perfectly rebuilds the original audio waveform. Each sample value appears at its sampling point, and the sum of all individual impulse responses between those points forms the smooth, continuous waveform. This overlapping of impulses fills in the gaps between samples, creating the full analog signal. When the filter removes the unwanted high-frequency components, the remaining waveform passes through the same points as the original, correctly filtered sound. In theory, a perfect low-pass filter can reproduce an output waveform that is exactly the same as the original band-limited input. The filter's impulse response is what allows these discrete samples to reconstruct the continuous sound. This shows that digital samples contain enough information to describe the parts of a waveform that occur between sampling points. The reconstruction works no matter where the samples fall in time, as long as the signal is band-limited. Increasing the sampling rate doesn't make this reconstruction more accurate. It only increases the number of samples within the same perfectly captured waveform. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Analog output filters often cause phase shift and distortion, so manufacturers replace them with digital filters. A digital filter is a circuit or algorithm that processes digital audio samples, taking them in and sending them out in a modified way to shape the sound. When used at the output of a digital audio system, a digital filter performs ideal low-pass filtering digitally, helping to rebuild the waveform before it becomes analog. Instead of removing unwanted high frequencies after digital to analog conversion, digital filters handle this task before conversion. Then, a simple analog filter removes any remaining high-frequency artifacts. Most digital filters used for this purpose are finite impulse response FIR filters. Oversampling makes the filter design simpler. It works by adding new sample points between the existing ones through interpolation, increasing the sample rate. The output signal, therefore, has a higher sampling frequency than the input. This process is usually implemented with a transversal filter, which uses a combination of delays, multipliers, and adders. An oversampling filter does two main things: resampling and interpolation. Resampling raises the sampling frequency by inserting zero samples between the originals, multiplying the sample rate by the interpolation ratio. Although the signal's spectrum stays the same, its sampling frequency increases. Interpolation then calculates the values of the missing points to create smoother transitions. For example, in quadruple sampling, the filter produces 4 samples for every original one. This also moves the unwanted spectral images further away from the audio band, allowing a simple, gentle analog filter to remove them easily without causing phase shifts or distortion. A digital filter shapes an audio signal based on its impulse response. When this response is made up of a limited number of points, the filter is called a finite impulse response FIR filter. In output low-pass filtering, oversampling is used to raise the Nyquist frequency, allowing better control of unwanted frequencies. After oversampling, unwanted spectral images are moved to much higher frequencies, where a simple analog low-pass filter can easily remove them. If the sampling rate is lower, these images sit closer to the audio range, requiring a steeper analog filter to separate them. However, steep analog filters can cause problems such as ripple, ringing, and phase distortion near the cutoff point. Because digital filters work entirely with numbers, their performance does not drift with temperature changes or aging, unlike analog filters. Digital filters can also be designed to have a linear phase response, meaning all frequencies are delayed equally. Additionally, any high-frequency loss caused by sampling errors can be corrected by adjusting the filter coefficients to slightly boost frequencies just before the cutoff point. Another major advantage of oversampling is that it helps lower quantization noise in the audible frequency range. Oversampling spreads the total noise across a wider frequency band, reducing the noise level within the audio range. Each time the sampling rate is doubled, the quantization noise floor drops by about 3 decibels. Noise shaping, also called spectral shaping, goes a step further by controlling where that noise appears in the frequency spectrum. It changes the frequency response of the quantization error without affecting the audio signal itself. This technique is commonly used in both AD and DA converters, often through sigma-delta modulation. Normally, quantization errors produce white noise, spread evenly across frequencies, but by designing the error feedback system carefully, the noise can be redirected toward less audible frequencies. Noise shaping works especially well with oversampling. Oversampling expands the bandwidth, giving extra space to move high-frequency noise out of the audio band. As frequency increases, quantization error also increases, pushing more noise outside the audible range. Noise shaping suppresses noise within the audio band, while shifting it to higher, inaudible frequencies that can later be filtered out. This trade-off, less noise in the audible range but more noise above it, is the core idea of noise shaping. Modern sigma-delta converters use both oversampling and noise shaping. For example, an oversampling AD converter may record an analog signal at a very high sampling rate with a 1-bit resolution, then convert it to 48 kHz and 16 bits for storage or processing, and finally oversample again for DA conversion. Noise shaping can also work without oversampling. In this case, the total noise power stays the same, but the noise is reshaped to match the ear's sensitivity curve. Some frequencies may have slightly higher noise, while others are quieter, making the noise less noticeable to human hearing. After the digital signal has been filtered, it is sent to a digital-to-analog converter, which changes the digital data back into an analog audio signal. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.